Howdy, everyone.
Good morning.
Good morning.
I hope you guys are having a good start to your day. Okay. Here's the thing that I need to do. There's a couple things that I need to do. I need to save that, so then that's done, so I don't lose that. All right. So the first thing that I'm gonna talk about is, well, we got our announcements. That's the one. Here's our Canvas page, the way I see it. Um, I posted an announcement on Monday after class, obviously. Well, maybe not obviously, but I posted it after class. I hope that everyone saw that, and I hope everyone is good on in terms of like not getting any fender benders or anything. Um, so there's a couple of things that I didn't go into in the announcement that I sent out regarding our classes structure and adjustments to the schedule. If you remember last Wednesday, I mentioned, hey, on Wednesday today, you'll have to sign on with SSO. And I did not enforce that today just because I wanted to, give us two actual class meetings. Because if someone joined late or, um, if someone joined late, then they'd have the opportunity to join the class and not be like, hey, I'm locked out. But starting on Monday, we will be using the SSO login. That link that I sent you guys, let's see, first lecture meeting. That's one place that you could get it. Be sure to join using SSO. So follow this link. This will give you some instructions on what you need to do. I see what web browser are you using? I have to use Google Chrome on my Mac since Safari won't work. Good morning. What does LTI tool missing mean? Okay, Grayson, that's a great question, and it's probably one that you're not the only person to see. Um, Chances are that is popping up because Proctorio is not in your web browser. It hasn't been installed or something of that nature. So I make sure that Chrome is up to date, and then give it another try. So that would be my best guess. But again, maybe not again, but make sure that you contact ITAC. It says all good when I click on the red part. Um, I'm not exactly sure what the red part is, so I can't really answer that any further. I'm sorry about that. But I would contact ITAC. Chrome is, I think that's the browser historically that has always worked for folks. Um, but I know with Macs, there are some instances where people have to like update or do like a software update on their operating system. So make sure that everything is up to date, and I would contact ITAC. Okay. Yeah, contact ITAC, send them screenshots and stuff and say, here's what I got. Okay, so we were wrapping up, or we were still working in chapter number one. So that's what we're going to do today. And we will then jump into chapter number two. Um, you have a discussion that will open today, the 28th at 12 p.m. You have a quiz that is open now. You have a Proctorio practice quiz, which if you did not do that over the weekend, you get another stab at it. The one this week will close on Sunday at 11:59 p.m. Um, and if you do that, you'll get half a bonus point on your final exam, total extra credit. Um, the quiz, I would make sure I would work on the Proctorio practice quiz first. No, you cannot use an index card for the quiz. If you click on the quiz, that also says in the description, quiz number one, remotely proctored. This quiz is closed note. You are not allowed to use any notes to help you when taking this quiz, not even the index card. This quiz, I'm happy that I've clicked on this because this quiz is due Friday the 30th, so this upcoming Friday at 11:59 p.m. After that, it is considered late. Now, with that said, you can still complete it, but there will be a late penalty. Now, that late penalty is 12.5% each day. So what that means is if you complete it on Saturday before 11:59 p.m. and you get a perfect score, it'll go in the grade book as an 87.5. And you can then complete it on Sunday. If you get a perfect score on it on Sunday, it'll go onto the grade book as a 75%, which it's out of 10 points, so a 7.5. Okay. I'm going to switch my share over to, I'm going to stop it. Then I'm going full screen on this. And I'm hoping that that doesn't do that thing that it did to me last time. Share. Okay, where are we in terms of our? Okay, great. 10. Okay, so what we were doing last time was we talked about classifying matter. We talked about physical and chemical properties. Do we have one quiz per week or two quizzes per week? You got one quiz a week. I'm happy that you asked that, Amy. Are we allowed to take the quiz after class? You are allowed to take the quiz basically whenever you want. Um, I'm going to go back to our Canvas homepage so that you guys can, so we can all look at this together. So here's our Canvas homepage. There's a part of the screen that's obscured. Okay. So this is not what you see in the app. This is what you see in a web browser. I'm going to view this as a student, so it's exactly what you guys see. This is our schedule for the entire semester. So we are on class day number 3. How about that? We've met one total time. This is number 2, and we're already 3 days done. We have a total of 29 meetings. Today is Wednesday, January 28th. We have a quiz that was moved from Monday to today. That is our quiz for the week. Here in this column right here, material for the day. Okay, material for the day in this column, if you scroll over January 28th, 2026, you'll see this first link, which is a PowerPoint link. So if you click that, if you're in a web browser, that'll open up as a PowerPoint file. If you click this PDF, that's usually a little bit more user-friendly in terms of if you're using a mobile device or something like that. Could anyone give me a letter in the chat if you have used the PDF in a mobile device during our class period? Okay, so I think maybe your most user-friendly thing in a mobile device is probably going to be the PDF, and that's our slide deck for the day. I just have it as a PDF as opposed to a PowerPoint file. So I've got both options there for you. What we're going to be starting with is chapter 1. Um, then if you look ahead, Monday, February 2nd, we've got our quiz number 2 that will open up on Monday and it will close down in the same sort of pattern. It's considered late after Wednesday. Um, and so, yeah, this is kind of the rundown. So this is quiz 2, quiz 3, quiz 4. I'm going to be adding a link for this practice exam, so you have that. That should be up no later than Monday. And that will cover all these learning objectives. What assessments are we allowed to use a note card for? Exams exclusively. Only exams. Great question. Thank you. Okay, cool. Well, then I'm going to switch back over. We do have a Zoom question today. Or we do have some Zoom questions, but one thing that I do want to say is, I want everyone to have a couple of opportunities, kind of practice opportunities to do answer a Zoom question. So today, everyone's going to be getting full credit for Zoom participation. If I see the participants drop from 120 to 70, though, I'm going to be suspicious. Is quiz 1 going over chapter 1 or both chapters 1 and chapter 2? It's only all your quizzes are going to be over stuff that we have covered in lecture. So it's only chapter number 1. Okay. All right. Oh, look, somebody joined. Great. Absolutely. Okay, so where are we? Slide deck, PowerPoint. I'm going to move my chat. Oh, somebody just left. We got to 121 and then we dropped down to 120. Okay, so Physical and chemical properties. We're talking about basically everything can has physical and chemical properties. Physical property can be observed without changing the identity, whereas a chemical property can only be observed by changing the identity. And what I want you to do is try to think about this as like something on the atomic or the molecular level, something at a very minuscule level. Um, just to give you the right framework to work with it. Some good examples are, well, color is a good physical property. Um, Whether something sinks or floats is a physical property. Chemical properties typically are going to be whether or not something reacts. So, fermentation is a good example of a chemical property. Now, physical versus chemical changes. Physical changes, well, ice melts, it changes state. A chemical change would be something like, and this is kind of a classic example, a candle burning. Now, this is one that people have a tendency to, well, actually, heck, give me a number in the chat if you feel like you've ever been guilty of, and guilty is a harsh word, but guilty of overthinking something. Give me a number in the chat. Yeah. This one is, everyone loves to overthink this one. Now, what I'd like you to do is thinking about this. Whenever I think of a candle, I think of two things. Or I think of like, what does a candle consist of? It consists of wax and it consists of a wick. Those two things. Now, whenever I burn a candle, is the wax burning? Y or N to the chat. And that's a little bit tricky, but no, the wax melts over time. It will melt, and you'll go from a candle that's this tall to basically just a puddle of hardness. So the wax melts. Does some of it burn? Maybe, but when you think about a candle, I want you to think about, and Vivian, you're absolutely right. The wick is what burns. So this is the sort of thing that it's not a trick question. But rather than thinking about the object and getting kind of jumbled into the object, try to think about the action verb, the word there, the burning. Try to translate that and say, okay, well, a candle burns. Oh, I know what that looks like. But let's take that action word, that word of burning, and let's apply it to something else. Um, a piece of paper, if that burns, what do I think that is? Is that something that's changing at like the molecular or the atomic level? Yeah, that's something that, you're not going to be able to pick up the ashes of a piece of paper and be able to use it again because, well, they're, I mean, if you can actually collect the ashes, most of them have completely been like destroyed and combusted. Could everyone give me a number in the chat if, oh, okay, I understand that one, or a letter in the chat if you're like, don't follow? Seeing lots of numbers. So I do see some letters though. I would just recommend that whenever you see a question that asks about a chemical change, think about the word that is the arguably the important one. And the object isn't really the important one. Instead, and not trying to make this an English class, but the verb, the action word is the important one. So when you see a question that asks about this, just kind of say, oh, a candle burning. Well, burning. And then the next one, rusting. Okay, okay, yeah. I don't care if it's a nail, I don't care if it's a bike chain, whatever. Okay. Now, the next thing that we talked about were our major states of matter. We talked about solids. Solids are very ordered and very organized. So they have physical properties that are different from other states of matter, like liquids and gases. Now, typically, whenever we see these states of matter, you'll see something denoted with an S in parentheses that indicates a solid, L indicates a liquid, and G indicates a gas. Now, there is another one that we'll introduce a little bit later. Well, I'll introduce it right now, but we'll go into a little bit more later on. And that is AQ, aqueous. Now, aqueous, I want you to think about this to indicate something dissolves. So a classic or a good example of something that you would see as AQ would be NaCl. Could anyone add to the chat what is NaCl? Salt. Perfect. Table salt. I saw a question I'm going to go back to. Would a metal burning, melting be considered a chemical change also? That's a great question. So, if a metal melts, that would be a physical change. I'm happy that you asked that, Isabella, because that brings us to this right here. NaCl. And I saw some other questions too. Okay, salt, sodium chloride, perfect, perfect, perfect. Table salt, table salt. Da, da, da. Okay, so whenever you see, like, let's say that you got NaCl, your table salt, and you sprinkled it into a glass of water. When that table salt is on, is in the salt shaker, you would denote that as a solid. Okay. Now, whenever you put that, could everyone give me a number in the chat if they follow? Yeah, table salt in a salt shaker is a solid. And then a letter if, wait, I don't understand that. Okay, so we got that as a solid. So NaCl, the solid. That's, if you spill it on a table, well, first of all, throw some behind your left shoulder for good luck. But also, whenever you can kind of think about it as there's no water there. So this is a solid. Now, when you add this to water, what happens is you have something occur at the molecular level that makes it different. When you add it to water, you get salt water. And that then changes to Na plus and Cl minus. Okay. Now, what I want you to think about that as is these pieces as a solid are held together really tightly, but then when there's some water, they just kind of disconnect. Now, this is a little bit tricky, but these two individual components, Na plus and Cl minus, they don't really change. That's weird, but they don't really change. So we would denote this as AQ when it's in water. Now, this is a little bit tricky, but if you got salt water, NaCl, sorry, if you got salt water, and that would be AQ, salt water, let me rephrase it. Salt water is NaCl, and you denote that with AQ, not L. Okay. And we'll talk more about this when we talk about solutions and solvents and everything like that. But I want you to understand that, well, when it dissolves, it doesn't become a liquid. Now, with that in mind, if NaCl, if you have that, I'm going to leave and join on my computer iPad. Okay. Okay. NaCl is a solid. Hmm. Do you think that a solid, I mean, heck, ice can melt into water. Does everyone agree with that? Just kind of, yeah, I think so. What do you have to do to get ice to melt? Well, you have to add heat. You have to add energy to it. NaCl here as a solid. If you got table salt and you heated it up, what would happen? Eventually, and with enough heat, that solid NaCl is going to turn to a liquid. Okay? That is different from aqueous NaCl in water. It's a subtle difference, but it's an important difference. So basically, anything can be a solid, a liquid, or a gas. Now, Isabella, I believe, asked the question about a metal melting, like gold, for instance. Um, could everyone give me a X in the chat if you believe that gold can be melted, and when it is melted, it's a liquid? It's a little weird to wrap your mind around, but seems like everyone agrees on that. In order for it to stay a liquid, it has to be very hot. Okay. Now, do you think that if you got gold hot enough, liquid gold hot enough, Could it convert to a gas? Y or N? Yeah, why not? I'm seeing lots of no's, but it absolutely could. Now, would it be extremely hot? Y or N? Absolutely. It would be extremely hot. Water, whenever it is a solid, melts. It has a melting point. Liquid water, when it turns to a gas, does anyone know what that is? That process is known as? I'll give you a hint. It starts with a B and ends with an oiling point or an oil. Absolutely. It will boil. Liquids boil and they turn into gases. It takes a lot more heat to get a liquid to turn into a gas than a solid to turn, sorry, liquid water to turn into a gas than solid water to turn into liquid. So everything can go through these different stages. Even though some of them it's like, oh yeah, I understand. I can agree with water doing that, but gold, no way. I don't think anyone should try any of these things. And when we talk about gold going from a liquid to a gas, that's going to be something that takes like 1,000 degrees or something like that. I'm not exactly sure what it is, but everything can convert from a solid to a liquid to a gas. Salt, table salt, can convert from a solid to a liquid to a gas. Okay, so we talked about these different states of matter. There are some important characteristics and features of these different states of matter. Solids have a definite shape and a definite volume. Liquids have an indefinite shape, but a definite volume. Gases, an indefinite shape and an indefinite volume. I made this little table down here to kind of use as a reference. We have solids, liquids, and gases. And then this right here would be shape and volume. So a solid has a fixed shape and a fixed volume, which is why we have checks by those. Liquids are going to not have a fixed shape, but a fixed volume. Gases won't have either. Now, the next level of organization and thought about types of matter, we can classify matter. So everything is going to be classified as either a substance or a mixture. Now, a substance can be a compound or it can be an element. An element is just going to be made up of one thing, of one specific element, whereas a compound is going to be composed of two or more elements. There are also mixtures. Now, it's easy to think about mixtures like tap water, for example. Tap water is an example of a homogeneous mixture. Whereas when you go down to the beach in Galveston or South Padre or something like that, and you scoop up some water, that's going to be a heterogeneous mixture because if you let that sit for long enough, some of the silt and sediment is going to, well, settle at the bottom of that glass. You might be able to look through it for a little bit, and if you wait long enough, oh, well, there's a layer of sand at the bottom. Now, that's not exclusive to solutions because solids can also be homogeneous or heterogeneous mixtures. Here's a good, what's called a macroscopic level view. We've got a ring here that's brass and silver. You can detect, you can visualize and see easily where the silver is compared to the brass. Now, as much as we're interested in what these mixtures look like here, what we're maybe more interested in is thinking about these things at the atomic level. Now, an element is composed of one type of atom. These terms atom and element, it's kind of it's going to take a little bit of time to get comfortable with those terms. But I always would recommend thinking about an atom as the simplest possible thing. Now, a compound, by comparison, is composed of two or more elements. Okay. Hmm. So an element is going to be the things that you see on the periodic table. And if you have two or more elements, as what we have here with water, well, we've got hydrogen or elements of hydrogen, atoms of hydrogen, and oxygen. Whereas in oxygen here, O2, The oxygen that you inhale is O2. That is considered an element, and it is made up of only one type of atom. You have two oxygen atoms. So whenever you're distinguishing a compound from an element, try to think about, well, what are the symbols that I'm seeing? Here, you see two identical red balls. Those two red identical balls represent oxygen atoms. Hence, this is an element. Gold here, well, that's just symbolized by AU. Okay, so here what we have is kind of a molecular view. This is a molecular view. And this right here would be a macro view. So this would be like a gold nugget or something like that. Or if you go to Costco, they sell gold. So think about what the thing is that looks like at the symbolic level and what is involved there. Okay. Atoms versus molecules. Okay. Now, if you look at these right here, on the right-hand side, we have water, carbon dioxide, and oxygen. Are all of these molecules? Yes. These are all molecules because they are composed of two or more atoms. Okay. Now, if you look at water, H2O, carbon dioxide, CO2, and oxygen, O2, do all of these have the same number of types of atoms? No. Oxygen has two identical oxygen atoms. Carbon dioxide has carbon and oxygen. Water is hydrogen and oxygen. So this is a little bit tricky, and I'm going to use oxygen as an example. Let's focus in on oxygen, O2. A molecule of O2 is also an element. Okay. So I'm going to add that molecule and element. Could everyone give me the number 7 in the chat if, hey, I follow that. Okay. Now, give me a Y or N. Can you apply the terms molecule and element to carbon dioxide? Y or N to the chat. Sorry, let me rephrase that. Can you correctly apply them? You can apply molecule because carbon dioxide is a molecule. Perfect. But is it an element? Now let's jump back to the previous slide. An element is composed of one type of atom. So now what I'm going to do is I'm going to get my eraser so I can clean this up a little bit. These two are molecules. And now I'm expanding my consideration to include water. These are molecules. Give me a 9 in the chat if you agree with that. Okay. And then the next part, but not elements. Give me a 3 in the chat if you agree with that and understand that. Okay. So these are subtle differences, and it's really kind of tricky to wrap your mind around that. But I think that if you try to visualize what are the atoms there and what are the symbols for those atoms, I think that's a helpful kind of starting point. So an atom is the smallest characteristic of an element. Gold, AU. Just between the 124 of us, is anyone give me a J in the chat if you've ever heard of the MTV show Jersey Shore? or if you've ever watched a movie that has like Goodfellas or something like that, every time I say the symbol for gold, AU, I always think of Jersey Shore and or the movie Goodfellas, or like a mafia movie where someone's like, "Hey you," and they're talking, trying to get someone's attention. And so I will do my best to not say gold or "Hey you," but it's hard. It's hard for me. Okay, thank you very much, Keanu. All right. So we've got a couple of things that we're juggling here. We're talking about matter. We're talking about classifying matter. We're talking about molecules versus atoms and elements versus compounds. I think what would be helpful, yes, Joe Pesci, perfect. My cousin Vinny, that's a movie to watch if you haven't watched it yet. Um, that apparently has like if you ever consider going to law school, I've heard my wife went to law school at Texas Tech, and she's an attorney, and I believe that in one of her classes they watch that because they have a very good demonstration of cross-examining a witness. Um, okay, anyway, this slide right here, elements versus compounds and atoms versus molecules, I wouldn't hesitate to make your own kind of consolidation of this. So oh, that's great. I would recommend thinking about elements versus compounds versus atoms versus molecules. Throw all of them together so then you're considering all of them, and try to apply terms to different things. So what we did here, H2O. Yeah, it's a molecule, but it's not an element. Okay? So then what could we do? Well, H2O is a compound and a molecule. Okay? Now, oxygen by comparison. Um, everyone agrees that it's a molecule. I don't know what happened to my writing there. Molecule. O2 is a molecule. We're good there. Is it a compound? Y or N to the chat. No, it's not. So do those sorts of things to like different substances. If we look at gold, well, gold's not a molecule and not a compound. Those are really good exercises for you for um, types of questions to anticipate on your exams. Okay. And actually, I'm going to bring this up to you guys. I think that it was brought up in my later class. Somebody said, "Hey, do you have any suggestions on how to study for this class?" And I was like, well, what I would do, like prepping for the exams and stuff, what I do is I'm giving you the slide decks that I'm using. Take those slide decks, put them into Chat GPT or Gemini, and say, write me a 30 question exam, 30 question multiple choice exam. Same thing goes. Gemini, if you have access to Gemini, Gemini is good about taking things out of YouTube videos. And so I'm posting all the recordings for this class. You will always have access to the YouTube links. Take the link and say, hey, based on this lecture, write a 5 question quiz. Just some thoughts. Okay. What would a gold bar be comprised of? That's a great question. Would be individual atoms of gold or what? That is a fantastic question, Jonathan. So if we think about gold, Maya, I see your question. I can come back to that in a second. If we look at gold, an individual atom of gold, well, that is an atom of gold. This is an element. This gold nugget is the macroscopic view of gold. If you were to shrink yourself down to the atomic level and say, what does that look like? It looks like this. That might seem a little bit weird, but um, this is just a bunch of gold atoms that are basically like linking arms. So a gold bar is gold atoms linked to one another. Now it's a little bit more complicated and complex than that. but that is what gold looks like at the atomic level if you take a gold bar or a gold nugget or something like that. I hope that answered your question, Jonathan. If it did not, please let me know. Next question. Isn't O2 a and molecules to that classified as diatomic? Okay. So O2, oxygen, is indeed a molecule. So we've got that, but it is not a compound because it only consists of oxygen. Now, is it classified as diatomic? Yes, it is. And we'll talk about diatomic gases and diatoms later on this semester. But yes, it is classified as a diatom. So when you have more than one atom, well, then it would be considered a molecule. So a diatom, like a diatomic substance, is a diatom, but it's also a molecule. I hope that answers your question, or uh, I hope that wasn't just a waste of time. Does that make sense, Maya? Next question. Okay, cool. Private message question. Could you give an example of something that's a compound but not a molecule? Okay, that's a great question. Something that is a molecule is composed of two or more atoms. Okay, so anything that has two or more atoms is a molecule. Now, if we go back to our definition of compound, it's composed of two or more elements. Now, if I were to just strike this right there, two or more, composed of two or more. If something is a compound, it is a molecule. So let me give you all molecules. Okay, let me make sure that I can write this properly. Okay. 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 All compounds are molecules. Could everyone give me the number 5 in the chat if you follow that? Okay. And then I'm going to add a little follow-up to that. But not all molecules are compounds. UNDS. Because if we look at oxygen, oxygen is a molecule but not a compound. Because O2 oxygen is an element. So the question that I was asked was, and just so I can circle back on this and make sure that I answer the question that I was asked, could you give an example of something that is a compound but not a molecule? And the answer to that question is no. Because if something is a compound, it is a molecule, but not all molecules are compounds. The person who sent me that private message, does that explanation make sense? And for anyone else, is there confusion there? Okay, I got it. Okay, cool. Okay, so now what we're going to do is we're going to shift a little bit and we're going to talk about measuring things. And when you think about measuring things, my first thought is like a ruler or a yardstick or something like that. But measurements are more than just that. We have a couple of different types of major measurements. We've got length, mass, volume, time, temperature, amount of a substance. These are the major units of measurement. Length, we have, or for all of these, we have what's known as the SI unit. And you can kind of think about this as the international unit. So if you went to France or if you went to uh, Peru, well, this meter, that's a part of the metric system. We use the imperial measurement system in the United States. But this is like, you could go into a chemistry lab in Peru, and then you could go into a chemistry lab in South Korea, and you're going to be talking about these particular units. Grams for the mass of something, as opposed to like pounds, because when you think about pounds, that it's not as simple as what is the mass of it. Volume, liters, time is measured in seconds, temperature is measured in Kelvin, and moles are the amount of a substance. So this one right here, actually, I'm going to go ahead and put these two. That's a star. There we go. There's a star. These two, Kelvin and moles, you could kind of think about those as like, oh, those are science terms. Um, and I want to give you a little bit of background here. This weekend, when it got to 22 degrees Fahrenheit, we'll say 22 degrees Fahrenheit. Um, if you looked at like the Weather Channel or Google or something like that, actually, I say Weather Channel, but I don't know that it really exists very much anymore. When I was a kid, I'd watch the Weather Channel hoping that I'd see snow flurries and be like, school's going to be canceled. And it never happened. I grew up in College Station, so I think I had like 3 snow days, K through 12. Okay, so we have 22 degrees Fahrenheit. Um, could anyone make an estimation as to what 22 degrees Fahrenheit is in degrees Celsius? I like it. -10. We'll go with that. I'm not sure exactly what it is, but yeah, the important point that I want you to take away from that is it's negative. Okay. Does that make sense? Okay. So these different scales, they're going to have different measurements. Um, if you go to Antarctica, could you tell me what do you think the temperature is in degrees Fahrenheit? And I say Antarctica, despite and knowing that it's like one of the largest continents. Um, we go to Antarctica City, where all the penguins live. So yeah, -30 degrees Fahrenheit. Okay. And when we talk about that in degrees Celsius, that's going to be something like I don't know, -45 degrees Celsius. Okay. Is everyone good with those numbers, roughly? Now, this right here, Kelvin. Kelvin is a temperature measurement scale that has no negative value. So if you go to the coldest place in all of Antarctica, it's never going to get below 0 in degrees Kelvin. When something has no negative value, this is described as being has it having a just a second, Jonathan, I'll get back to that. This is considered an absolute scale. If you've ever heard of absolute zero, that is like a hypothetical temperature that can be achieved. Um, if you put something in the back of your freezer, well, it's going to get to like, oh yeah, it's going to get like, I don't know, we'll call it 4 degrees Celsius or 4 degrees Fahrenheit. So it's going to be like -30 or something like that. But in terms of how a chemist or a physicist looks at that, you might be like, oh my gosh, that's the coldest popsicle ever. A chemist or a physicist is going to be like, yeah, I've seen colder. And you're like, no, it's frozen. And they're going to be like, yeah, at the atomic level, nothing really interesting is happening. There's some movement, but it's not absolute zero. Okay. So the Kelvin scale is particularly unique because there's no negative temperature. Does that make sense? Or can you, rather than does that make sense, can you guys accept that? I'll go with that. Okay, cool. Now, I see a question. I'm going to answer a question. Jonathan, can you differentiate mass and grams, or mass/grams, amount of substance, moles, and weight? Absolutely. I will do my best to do that. So, when we talk about um, mass versus weight versus moles. These are the big measurements in terms of like a chemical reaction or something like that. Well, weight is if you've ever thought about or I remember in elementary school reading books about or seeing books about other planets. You learn about gravity on other planets, the gravitational pull. So give me a Y or N in the chat if you're familiar with the idea that, hey, Joel weighs 230 pounds on Earth, but if I went to the moon, then I wouldn't weigh that much. Okay. And that's just because the gravitational force or the gravity on Earth is different from that on the moon. If I went to Jupiter, that'd be a bad idea because then I'd just get stupider. I have kids in elementary school, so I hear that one. So I wouldn't want to go to Jupiter for that reason, but also I don't know what the gravitational force is. So that's weight. Weight has the factor of gravity. Now that's why we use pounds for that. Pounds are related to gravity. Now, mass versus weight. Well, if I'm on Earth and then I go to the moon, my mass does not change at all. The like everything that is me does not change. My weight changes, but my mass does not. Okay. Now, mass versus moles. I think that this is the best thing to think about because chemists are most interested in, and maybe I would go as far as to say scientists in general are most interested in moles because they want to know about like chemical reactions. Um, and so they kind of look at the parts that make something up. So whenever this is thinking about, well, how many molecules or atoms make something up? And I'm happy that you asked that question. But before I proceed, um, does that give me a on a scale of 1 to 5, one being that covers it perfectly, and a five being I still don't know the difference. Could everyone give me a score on that? Okay. Now, some of these things will get a little bit more clear. What we're going to be focusing on most in this class is mass and moles, and we'll differentiate between those two. So, one way that I think about it is I like to think about Oreo cookies, just in general. When I'm hanging out and I'm like, oh, I gotta go do X, Y, and Z, Oreos. I love Oreos. I do, no doubt. I love Oreos. Whenever I think about an Oreo cookie has three parts, as far as I'm concerned. It's got the two wafers, and then it's got the cream disc wafer thing. So I think about that and I say, okay, well, one Oreo is made up of three things. Now, those are true statements. Does an Oreo have a mass? If I put an Oreo onto a digital balance and I got the weight of it, I would be able to see, oh, an Oreo is 46 grams, just throwing a number out there. So all of these things are true and they are related to one another. Now, that's just kind of a model or example. But now, what I want to do, does everything have mass? Yes, it does. Some things have more, some things have less. But yeah, everything has mass. And yeah, I see your question. You're just kind of affirming. Yes, everything is going to have mass. But like thoughts don't, but maybe they do. We're not going to turn this into a philosophy class, so don't worry about that. Now, with that said, when we think about moles, a mole, and we will get deeper into this later on, but I want you to think about a mole as being like a dozen. If I gave you a dozen pennies, how many pennies do you have? Add it to the chat. Perfect. 12. If I gave you a, let's see, trying to think of another number. Well, if I gave you, okay, if I gave you a dozen donuts, you have 12 donuts. If I gave you a dozen dollar bills, you have $12 bills. Dozen is the defining word. Now, a mole of something. Um, if I gave you a mole of dollar bills, this is how many dollar bills I would give you. So 1 mole of anything, yes, you would, Grayson. And I would like sharing because sharing is caring. Um, if I gave you a mole of pennies, you'd still be rich because that's a lot. And if you think about this, okay, I always like to do this. Okay, so that would be okay. We're talking about 100,000 there. We're talking about millions, billions, trillions, quadrillions, pentillions. So I believe that 602 pentillion something is 1 mole of something. Now, this number and remembering pentillion is kind of not super fun. So rather than using that, we use something known as scientific notation. So what we will do is generally we're not going to say, okay, 1 mole is this many particles, write all of this out. Instead, what we're going to do is say, okay, use scientific notation. Now, scientific notation has a kind of it has a structure to it. So writing this number right here, in scientific notation, what we're going to do is we're going to take the first non-zero digit, which is a 6, and then we're going to put a decimal. And then we're going to look for our second non-zero digit. And we're going to write this. Well, O2. Okay, does everyone agree with that, including all of the non-zero digits in this number? Okay, 6.02. And then, I want to account for all of the zeros because they matter. Because if someone's like, hey, I'm going to give you a mole of dollar bills, and then they give me $6.02, I'm going to be like, you forgot a bunch of zeros there. You forgot actually 21 zeros. So 6.02 times 10 to the 23rd is the number that we use. And I will say that, and we will say that so much this semester that it will be kind of like muscle memory. 6.02 times 10 to the 23rd. Now, that is scientific notation. What we can do with that is simplify big numbers. Grayson got ahead of us here. I'm not saying that in like a backhanded or disrespectful way, but yeah, you jumped and you said, okay, well, 8.67. Well, 8.6. Okay. I have a private message question asking about the number of zeros. Why 23? Okay. Now, before I do that, or actually, no, I'm going to do that right now. I want you to look at this number and imagine, well, where is our decimal place? Where is our decimal? It's right here. If I want to write this number as 6.02, I have to move this decimal. How many times do I move it? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. So I moved it 23 places. So that's where 6.02 times 10 to the 23rd came from. Now, if we go to our next example, write 8675309, which that was a popular song. I think I was like 3 or something like that. 8675309. Jenny, Jenny, who can I turn to? I don't know. Well, your decimal is effectively right here. So we're going to move 1, 2, 3, 4, 5, 6. So 8.6 times 10 to the 6th. Okay. So I've got an exponent there that's positive. The way that I like to think about this, and if you look at these different options, we're going to come back to these in just a second, but looking at this one right here, that's a negative exponent. Well, what do I do with a negative exponent? Now, the way that I think about this is if the scientific notation has a positive exponent, The number. Gosh, sometimes my handwriting is not great, and then sometimes it's just horrible. The number with a positive exponent is greater than 1. So that means that if it's a negative exponent, the number is less than 1. So when you see 2.4 times 10 to the positive third, we'll rewrite this. We're going to move the decimal. In this case, since we see a positive exponent, we're converting from scientific notation to full notation. We're going to move the decimal with a positive exponent to the right. So rewriting 2.4 times 10 to the third would be 2, 4. Then it's 1, 2, 3. So 0, 0. So this question, which number is largest? Well, 2,400 versus 240 versus 24,000. And now answer option D. With a negative exponent, we're going to move this 1, 2, 3. So we've got 0.0024. I think Grayson was the first person I saw put that in there. You're absolutely right. Okay. So this takes a little bit of practice, and it takes a little bit of like, okay, what am I doing? Because my rules are going to be different. If I'm going from scientific notation to full and I have a positive exponent, I'm moving my decimal to the right. What about if I'm going from full notation to scientific notation? Okay. Well, then I'm going to be moving my decimal to the left, but that's still going to be a positive exponent. So give yourself examples like 4.2 times 10 to the third and 4.2 times 10 to the negative third. Well, 1, 2, 3, so 4,200 versus 1, 2, 3, 0, I'll put the decimal, 0, 0, 4, 2. And then these are scientific notation to full. Take full notation, 0.007, convert that to scientific notation. In this case, I'm going 1, 2, 3. So from full notation to scientific notation, that's going to be 7 times 10 to the negative third. It tends to, like, I always like to say scientific notation to full notation or full notation to scientific notation. Full notation is where every single number is written. Scientific notation is where I've simplified the number. Okay, now when we move on to this next one, and we're doing this. Write this number, 0.0000123. I might have said too many zeros. Well, this number is smaller than 1. Would everyone agree with that? Give me a Y or an N to the chat. So now I'm going into scientific notation. So I'm going to go ahead and write out times 10. And I might just go ahead and say, well, it's smaller than 1, so I'm expecting a negative exponent. 1, 2, 3, 4, 5 times 10 to the negative fifth. 1.23. Now, I have had folks in the past say, well, I want to write it as 12.3 times 10 to the negative sixth. And to that, I say, well, that's not the convention that's used. And so, are you going to, am I going to have questions on the exam that compare this and this? Probably not. If you use this, are you going to be like laughed out of the room? No. But I'm just trying to impress upon you and stress that the convention is number, period, number, 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 number. however many there are. So just kind of keep that in mind. Now, next up is which one is the smallest? Here we've got 2400, 0.024, 0.00024, and then 2.4 times 10 to the negative third. 1, 2, 3. So 0, 0. Okay, and I think I saw two questions. Can we have a blank sheet of paper on quizzes and exams to work on these sorts of problems? 100%. Absolutely. Scratch paper is completely allowed. Okay. So I would say that scientific notation is a skill and it takes practice. It takes refining that skill, and giving yourself examples and trying to see those numbers like, next time you buy something, look at the receipt. No, well, I spent $16.43. Let's write that in scientific notation. 1.63 or 643 times 10 to the first, because I moved the decimal one place. Okay. Now, large measurements versus small measurements. In addition to scientific notation, where we have these vast numbers, we also are going to see prefixes using the metric scale. Okay, so I'm going to come back to this slide because what I want to show you guys right now, okay, we had 8675309 to 8.6 times 10 to the 6, but will we change it back to 86, or let's see, what would that be? 8.6 million? Is that an issue on that we cut out those numbers? That is a great question, Isabella. And I mean, for this, I just went ahead and wrote 8.6. Anytime you have a non-zero digit, you do want to include those. So it would be more accurate to write this, or it would be better to write this as 8.675309 times 10 to the 6. That would be more accurate because these non-zero digits are true. It's kind of like, you know, I always tend to translate things into money. And I always think about it as like, let's say that I had $8,675,309 and I gave it to someone. And I was like, hey, I need that money back tomorrow. And they're like, okay, cool. And then the next day they came back and they're like, good news, I've got your $8.6 million. I don't know about you guys, but I would probably be like, hey, yeah, that's great. I'm excited that we're talking about millions, but what about my $75,309? And they'd be like, scratch offs? And I'd be like, bad idea. Should we be more accurate when it comes to exams and things like this, or is it okay if we put 8.6? The answers for the multiple choice questions will be more precise. So you don't have to worry about that. And if you see a number like this, if you see the converting from full notation to scientific notation, and you're like, wait a minute, we lost a lot of precision there or accuracy there, that's kind of a clue that, hey, that one might not be the best answer. And that's another way I want you to think about some exam questions, not necessarily is this right and is this wrong, but instead try to think about it as, is this the best answer? Okay, now we're going to proceed. Okay, so we've got metric prefixes. The most common ones that you will see are pretty much these three. If you've ever watched Breaking Bad or any other TV show where drugs are being moved, chances are they're talking about this prefix right here, kilo. 1 kilo of anything is 1,000 of something. I have a kilo dollars. Nobody says that, but they could. You got $1,000. Great. Now, these prefixes correspond to numbers. What I always try to do is, and what I want you guys to know is I want you to know the range from mega all the way to micro. I want you to be able to convert between those two. And I said this last time, but if you're looking at the clock and you're looking at we're on slide 28 of 45 and you're like, oh my gosh, this guy's going to rush us through the last 17 slides. I'm not. I built in buffers over the course of the semester, so I'm not going to lose any sleep over that. And I don't want you guys to stress about, oh, but what about this? there are today's discussion, for example, it might ask you to look at the slide deck, like look ahead. But most of the time, those slide decks or most of those things are really just like participation. So I don't want you to be like, oh my gosh, I have to. Okay. So anyway, um, if we look at these prefixes, mega, kilo, hecto, deca, deci, centi, milli, micro, some of these things might be a little bit familiar. For instance, centimeters. Okay, that's on one side of the ruler. Milligrams. I've got a dietary supplement here that has 750 milligrams. That wasn't really visible, I don't think. I want you guys to be able to take those numbers and convert them into different units. For example, 750 milligrams. If you were to look at this scale and say, well, what's in the middle here? What's in the middle is the base unit. That base unit is a gram. So decigram, centigram, milligram, microgram. And then you could go in the other direction. Um, think about these things and say, okay, well, 750 milligrams. How does a milligram relate to a gram? Well, what I want you guys to think about is that there are how many of that unit are in the base unit. So if I ask you how many grams, number of grams in 1 kilogram, can you guys answer that in chat? And again, this is some of these things I want you to think about. Like, have I seen this in pop culture? Have I seen this in a movie? And I'm seeing lots of people say 1,000. You're absolutely right. There are 1,000 grams in 1 kilogram. Okay. How many grams are in 1 megagram, which is going to be a capital M and a lowercase g? I've never heard of, I can't think of a movie I've seen where they talk about a megagram, but like a megabyte, for example. And computers are a little bit funky, so that's off. But yeah, a milli. Okay. What did we do? We related our number of grams to this larger unit. Now, what about milligrams? 750 milligrams. If you look at mg right here, and you compare that to our base unit, G, right here. Okay, I'm going to go back up here, mg and kg. It seems like everyone is kind of good with, yeah, there's 1,000 grams in 1 kilogram. Now what I want you to do is say, if you have 1 gram of a substance, how many milligrams of that substance do you have? If you have 1 gram, okay, I'm seeing people put this number in, and that's tempting. And this is a little bit funky, but if you have 1 gram of a substance, that means you have 1,000 milligrams of that substance. Okay, I see some folks who got that one. Good. So now let's convert 750 milligrams to grams. Tell me that number using exponents. Sorry, not with exponents, but just convert this to grams. That one would actually be 0. Yep, I'm seeing it. Yep, 0.75. 0 grams is 750 milligrams. Now, just a little bit of a tell here. I want you to know these ranges. Megagrams or mega all the way to micro. More times than not, questions that I will ask will relate kilograms and grams and milligrams and grams. Why is that? Well, those are the things that people encounter most often. If you get a dietary supplement or a multivitamin, chances are that multivitamin is going to have active ingredients in the milligram amounts. So that's why that's the one that I think is maybe most relevant. Now, we've got these prefixes that we use. Some of them can be a little bit confusing. Lowercase g indicates gram. Capital G corresponds to a prefix. Lowercase k corresponds to a prefix, kilo. Capital K corresponds to that temperature measurement of Kelvin. M, lowercase m is for meter or milli, which is why when you measure millimeters. And then capital M is going to be mega. Okay, so got a couple minutes left. Good, 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 good. Now, when we're actually measuring the mass of something, what is the mass of this apple in scientific notation? This apple has a mass of 172.3 grams. If we were to write this using scientific notation conventions, we're going to say 1.723 times 10 to the 1, 2. Okay. Now, what about if this was not using grams, but instead kilograms? So how would we convert this 172.3 grams to kilograms? Well, there are 1,000 grams in 1 kg. So this would be, you're absolutely right, Jonathan, 0.1723 kg. Because if 1,000 grams make up 1 kilogram, 172 is less than 1,000, we would say 0.172. I got you, Aaron. Okay, so that's how we measure mass. Now, measuring volume. This right here is what is known as a graduated cylinder. The volume of this liquid is measured in milliliters. So, could anyone tell me in the chat how many milliliters are in 1 liter? And just to give you a little bit of a guide, yes, our base unit is liter. Perfect. So 1,000 milliliters is equal to 1 liter. Now, what does this show? Well, here's 50 is the top measurement, 40, this would be about 45 milliliters, ml. So if we were to convert that into liters, we would say, well, 0.045 liters. Like I said, converting between like milliliters, milligrams, and grams, milliliters and liters, that I think is going to be very helpful. Think about those sorts of things. The next time you grab I don't have one, surprisingly. Next time you get a soft drink, look at the bottle, and you're probably going to see something like a 20-ounce bottle is about, I think it's 535 milliliters. Okay, what does that say? Well, if you convert that, that would be 0.535. A&W root beer would be a great root beer that you could get. Thank you, Jonathan. Zero sugar A&W root beer, no less. A&W. Okay, measuring length of something. Well, we've got two different measurements here. We've got centimeters, and then on this side, it's going to be inches. Now, what is the length of this in centimeters? Well, that would be about 17 point, I'm going to call that 3 centimeters. 1 inch is 2.54 centimeters. Now that's not a conversion. This is not a unit that I want you guys to like keep memorized or anything like that, because that's going from imperial measurement to metric measurement. But if I gave you this number, I'd want you to be able to say, oh, okay, well, I could calculate the length of this pencil in inches. And you'd say 17.3 divided by 2.54. And that would approximately be, let's see, nearly 7, like 6.8. All right. Now, seconds. How many seconds are in 6.5 minutes? Well, 1 minute is 60 seconds. Now, I'm going to, let's see. Yeah, so let's see. Okay. We're going to get through this next one, measuring temperature. Temperature that we are going to be focusing on or the two temperature measurements are going to be degrees Celsius and Kelvin. Those are the two that we are most interested in and will be most interested in this class. What is this temperature in Kelvin? Okay, so this is 32.7. All that you do to take degrees Celsius to Kelvin is you add 273. So this would be approximately 305.7 Kelvin. Now, one thing that's worth noting is this little circle right here is called a knot, Naught. You don't use that whenever you talk about temperature in Kelvin. You just write capital K. So then another way to solve, or another way to think about this sort of question is right up here. Which temperature is higher, 25 degrees Celsius or 25 Kelvin? A or B? And this is a little bit tricky because, okay, well, what does that mean? Okay, so 32.7 degrees Celsius is like 85 degrees Fahrenheit. So that's a nice spring day. That is the same. So 32.7 equals 85 degrees Fahrenheit, roughly, equals 305 Kelvin. 25 Kelvin is going to be like negative 250 degrees Celsius. So pretty brisk, pretty chilly. Now, comparing all of these scales, this is what it looks like. We've got our degrees Fahrenheit. We've got our boiling point of water at 212, freezing point of water, 32. Celsius and Kelvin, Kelvin is the absolute scale. The lowest temperature Kelvin is 0. Lowest temperature Celsius is negative 273. And again, this is kind of like a theoretical temperature. Now, I'm going to go to post up a poll question or post up a question. And that's not it. That's not the one. This is the one. These are about the next thing, density. There's two questions here. I just want to give you guys the opportunity to answer a question. Everyone's getting participation credit for Zoom today. So it doesn't really matter what you answer this as. I just want to give you guys the chance to like see how it looks on your computer or whatever you're using. That's where we're stopping today. I'm going to do the same thing on Monday, but remember on Monday we'll have the SSO is going to be required. Your discussion point for today does lean into the next chapter or the slide deck that we didn't get to today, but I think that it's still something that you guys can do. So if you have too much of an issue with it, I've got office hours starting at 12:30. You can feel free to drop by those, or shoot me an email. And that'll do it. Again, I don't want you to stress about, oh my gosh, we're behind. I'm not stressing about it. And we missed a day of school, so that's a little bit funky, but we're going to be fine. And we're going to start off with density on Monday. Monday. So knock out density and then go on to the next stuff, the chapter 2 stuff. But I hope you guys have a great rest of your week. I'll see you on Monday, provided that there's no crazy weather mishaps or anything like that. Everyone stay warm, stay safe, and I'll see you guys. Does the quiz cover what we worked on in class and not density, but we haven't talked about? Okay, so I'm gonna stop my share. The quiz that is available right now only covers stuff from last week. So it's none of the new stuff. It's none of what we covered today. Then the next thing is a question posed of where do we find our Zoom recordings? Well, Zoom recordings, I'm going to do my share of my web browser. Recording for the day. So I'll go to view as a student. If you're looking at this on a web browser, one of the things that you're going to see is these columns: meeting number, day, date, graded activity for the day, material for the day, recording for the day. Um, I will post a link right here. You might not be able to see. I'm going to draw an X. I'll post a link right there whenever I have that link later today. And that's where it's going to be. And that's where they're always going to be, in that column. So I would expect the recording by like, no later than 10 p.m. tonight. I just say that because I've got class after this, and then I've got another class, and it always takes a little bit of time for the video to um, be produced. Okay, it looks like everyone's participated, so I'm gonna go ahead and end the poll. I'm gonna stop my share, and I'm gonna go ahead and say, not yet, not yet to what? Okay, well, I'm sorry I can't reopen it. It everyone's getting credit for today's poll, so don't worry about it from a credit perspective. Instead, I just want to make sure that you could see. If you could see the poll questions, then you're good. Okay, that's all I need to know. And everyone's getting credit for participating in the poll questions today. Okay. All right. Well, have a great weekend, and I will see you guys on Monday.